Alright, so let's try this one out. We've got the two sides, so I'm going to square those and add them together. And they're going to equal the hypotenuse squared. Get rid of that diagram. And then if you want to use the shortcuts, I mean, go ahead, it's up to you. Or you can FOIL the binomials times each other. I'm going to go ahead and use the shortcuts. First one squared is 4x squared. The product is 8x, but when you double it, it's 16x. And then the last number squared is 16. Same thing over here. First one squared is 9x squared. The product is negative 12x. If you double it, it's negative 24x. And if you square that last number, that's also plus 16. I'll simplify the terms on the left-hand side. That gives me 5x squared plus 16x plus 16. On the right, I get 9x squared minus 24x plus 16. Now I'm going to move everything to the right this time because I want my x squared term to be positive. So I'll subtract the 5x squared from both sides, and I'll get everything out of the left-hand side by subtracting it. So I get 0 on the left, which is what I want when I'm solving a nonlinear. You want it to be compared to 0. 9x squared minus 5x squared is 4x squared. Minus 24x minus 16x is minus 40x. And this is a nice little treat. 16s cancel completely, so now I don't have a trinomial. I don't have to use the AC method. All I have to do to factor this is pull out the GCF, which is 4x, and it's considered factored. So I have two possibilities. 4x could equal 0, in which case x would have to be 0, or x minus 10 would have to be 0, meaning x is 10. Now the original problem had a height of x. Well, not much of a triangle if x is equal to 0. So my answer by default has to be x equals 10. So there's the height of that triangle. The base of the triangle was 2 times 10 plus 4. So that's 2 times 10 is 20. 20 plus 4 is 24. And then the hypotenuse, if you recall, was 3x minus 4. 3x minus 4, 3 times 10 is 30, minus 4 is 26. So there are the dimensions of this right triangle. And we can check them really quick. 10 squared plus 24 squared is supposed to be 26 squared. Well, that's 100. That is 576. And that is 676. And sure enough, they are equal to each other. Does this triangle look familiar to anything we talked about earlier? 10, 24, 26?
Is that the 5, 12, 13 one?
Exactly, right. 5, 12, 13. It's just the 5, 12, 13, it's been doubled. That's it. It's still in the ratio of 5 to 12 to 13. So it's technically a 5, 12, 13 triangle. But again, when you put it into an algebra problem, you have these nice happy numbers with no ugly decimals or anything like that. So that's one of the reasons you'll see these types of triangles quite often. All right, so that's the last of the Pythagorean ones. The next